3.2, harmonic resonance. Recall from our solution before that omega n was not equal to omega, because if we had omega n equal to omega, we had a 0 on the bottom, and that x function became undefined. So that helped us get a solution in time, but what happens if we set that omega n equal to omega? If you set omega n equal to omega, you get resonance. Right? And resonance can be good, resonance can be bad, but it's a way to keep a lot of energy at a single frequency in the system. So mathematically, it means that the amplitude of the vibration becomes unbounded, right? That's what we get with that undefined value. And in the prior choice of x cosine omega t, which again is something that we chose arbitrarily, but if we stick with that, the particular solution fails. And so all we have is, it fails as a solution, right? So we have to get a new particular solution. We need a new particular solution at omega n is equal to omega. Right, so we're going to assume a new solution that comes from a variety of things, also just experimental knowledge. And we're going to say that in this particular case, x of p for a given time t, that's our particular solution, is equal to lowercase t, capital X, sine of omega t. Substituting that into the equation of motion in standard form and solving for x leads to x of p for a given time t is equal to f naught over 2 omega t sine of omega t. If you look at this, you'll notice that we have an issue, which is that this t here is time, and it's outside of the sine function, which means it will eventually go to infinity, right? So we have a particular solution, x of p, that is going to infinity. Not what we want, right? That is a vibrating system that goes in one direction for infinity. But let's see how we can still work with that. First, let's put this back with our homogeneous solution. So if we put it back with our homogeneous solution, we have x of t. Let's pull out our good friend capital A1 sine of omega t. Plus A2 cosine of omega t plus f naught over 2 omega t sine of omega t. Now, for capital A1 and capital A subscript 1, capital A subscript 2, we have to take the derivative, get velocity, take the derivative, get acceleration, apply our constants, x naught and b naught. We know how to do that, so let's just write the answer, right? The full solution of this becomes x of t is equal to v naught over omega sine of omega t. So we still have some oscillation there, plus x naught cosine of omega t I still have an oscillation. All is good. Plus F naught over 2 omega. So that adds some amplitude, but it's bounded. And then I have my problematic T, which grows to infinity, sine of omega T. So if I were to go ahead and plot this out, I might have something that looks like this. Time in seconds. And let's go amplitude, millimeters, but doesn't particularly matter. And let's just go, I've got a 0 line. And I might have something that looks a bit like this. That doesn't look so detrimental. Let's try that again. Let's try a faster frequency system. Whoop. There we go. That looks more devastating, right? It's going to keep growing and growing and growing and growing. We have oscillations in the term, but if you take out all of the terms that oscillate, everything related to sine, what you're left with is, let's go red because it's bad. I want a straight line. Sorry. My attempt to draw a straight line. You have these bounding terms that are F naught over 2 omega T. And technically you'll have negative F naught over 2 omega T. And those will continue to grow and grow and grow and grow and grow indefinitely. So if this was true and something went into resonance, it would always fail. What's missing in this system that's missing in all real world systems? No damping. If we add damping, we can constrain the resonance, maybe into something useful, right? But if we don't have damping, everything once you get it excited at the right frequency will fall apart. And if you keep it excited there. So it does take time to grow.